All right, so today we're taking a deep dive into probability. We've got a stack of textbook excerpts here, and I'll admit, at first glance, I thought this could be a bit dry. But the more I dug in, the more I realized how fascinating and surprisingly relevant to our lives probability really is.
It really is. We often encounter probability in our everyday lives without even realizing it.
Totally. Like, just think about flipping a coin, heads or tails, that classic 50-50 chance. It's almost a cliche at this point, but it perfectly illustrates the basic idea behind probability.
It does. That simple coin toss is a great example of what we call equally likely outcomes. And it's amazing how we can take this really basic idea and use it for like all sorts of more complex stuff.
Yeah.
Predicting things in economics, biology, even like traffic patterns.
Whoa, hold on. So you're saying with probability, I could like finally crack the code on rush hour traffic. Okay, I'm kidding, mostly. But seriously, if we're moving past basic coin flips here, how do we even define probability in a way that, applies to real life?
Yeah, good question. So when we talk about probability, there are actually two main types we usually think about: experimental and theoretical. Experimental probability is, well, exactly what it sounds like. It's all about actually doing the experiment. You flip the coin a bunch of times, you see how often you get heads, and that gives you your experimental probability.
So, like, it's the hands-on approach. Run the experiment, see what happens, and bam, there's your probability.
Pretty much.
Yeah.
But sometimes we can't actually run the experiment over and over again. I mean, imagine trying to figure out the probability as an earthquake to test like how strong a building is. We can't just go around causing earthquakes. And that's where theoretical probability comes in.
Okay, so if I'm getting this right, theoretical probability is less about actual testing and more about like using math to predict those odds.
Exactly. It uses math to calculate the likelihood of something happening based on all the possible outcomes. Like with that coin flip, we know there are two possible outcomes, heads or tails. And assuming it's a fair coin, each outcome is equally likely.
Makes sense. But I do have to ask about this formula I'm seeing in our sources. It mentions favorable outcomes. What's that all about?
Oh yeah, the actual formula for theoretical probability is pretty straightforward. It's the number of favorable outcomes divided by the total number of possible outcomes. So going back to our coin example, if we want the probability of getting heads, there's one favorable outcome, heads, out of two total possible outcomes.
Okay, so 1 over 2, which equals a probability of 0.5 or 50%, that lines up with what we know about coin flips. But I'm guessing things aren't always as neat and tidy as a coin flip, right?
Real life can get messy, and that's something important to keep in mind when we're talking about probability. And speaking of real life, one of our sources mentions this guy, Cardan, who wrote a whole book on probability back in the 16th century. The book on games of chance, he called it. Seems like he was onto something.
From gambling to, well, I'm guessing everything else, right? Because we've talked about earthquakes and traffic and all sorts of stuff. It's amazing how these ideas about predicting outcomes, which, started with games of chance, have evolved so much.
It really is. Probability is such a powerful tool now. We use it in so many different fields.
So it seems like we've gone way past just calling coin tosses, huh? This is already making my brain do flips, and we're just getting started. Okay, so probability helps us make sense of a world full of uncertainty, but how does this actually play out in, like, real-life scenarios? I'm looking at these examples in our sources about, like, marbles and birthdays, and I gotta admit, some of this stuff is kind of blowing my mind.
Yeah, those examples are a really great way to like wrap your head around these concepts, maybe without making your head spin too much. So let's start with something simple, like that bag of marbles in example 8. It's kind of a classic way to illustrate how simple probability works. You've got, say, a mix of blue, white, and red marbles, all jumbled together, 3 blue, 2 white, and 4 red to be exact.
Okay, yeah, I can picture that. Takes me back to being a kid, digging through a bag of marbles, hoping for that one special color.
Exactly. So let's say we want to figure out the probability of picking a white marble at random from that bag. Well, we've got 2 white marbles out of a total of 9 marbles, right?
Right. 2 out of 9, not exactly the best odds if I'm really gunning for a white marble.
Nope, definitely not. But that's probability for you. It's all about the proportion, In this case, it's the proportion of what we want those 2 white marbles compared to all the possibilities, all 9 marbles in the bag.
So 2 over 9, like we said. And that same idea applies to the blue and red marbles too, right?
Absolutely. And here's something interesting. If you were to add up the probabilities of picking each color, so basically all the possible outcomes in our bag of marbles, they'll always add up to 1.
1 meaning
100%.
meaning you got a 100% chance of getting some color marble, unless the bag's empty, of course. Laughs, exactly. Now let's move on to something a little bit more, shall we say, intriguing. I think you'll find this next one pretty interesting. It's called the birthday problem. At least that's what our sources call it in example 6. It really highlights how probability isn't always intuitive.
Okay, hit me with it. What's so mind-blowing about birthdays?
So imagine you're in a room with 23 people. What would you say the chances are of 2 of those people sharing the same birthday?
23 people.
Yeah,
Honestly, I'd say the chances are pretty slim.
you'd think so, right? But here's the thing with just 23 people, there's actually a greater than 50% chance of 2 people sharing a birthday.
Wait, are you serious? That seems like impossible.
It does, doesn't it? It feels totally counterintuitive, but it all comes down to how we calculate the probability. See, you're not calculating the odds of one specific birthday, but the odds of any 2 birthdays matching out of 23 people.
Okay, I think I'm starting to get it.
It's kind of like, imagine drawing lines between everyone in that room and seeing if any of those lines intersect. With 23 people, you're drawing a lot of lines. Okay, that is seriously wild. You officially blew my mind. This is why I love doing these deep dives. You just never know what kind of crazy stuff you're going to learn.
Nice. And that's just one example. The birthday problem actually comes up in things like database analysis and cryptography. It even helps explain why we tend to see more coincidences when we're dealing with large groups. But speaking of surprising scenarios, those dice-throwing examples in our sources, especially examples 10 and 13, those bring in a whole other level of complexity.
Yeah, because now you've got 2 dice. So instead of 6 sides, you've got...
Well, it's got to be more than double the possibilities.
Right. You've got to consider all the possible combinations you could get. Each roll has 6 possible outcomes, and with 2 dice, you have to account for every single pairing.
So 36 possible combinations, if my math's right.
Exactly.
So am I right in thinking that, like, rolling a specific number, like a 7, is different from rolling a specific combination, like a 1 and a 6, even though they both add up to 7? That's a great question, and you've hit on a really important point. You see, even though the end result might be the same, the path to get there actually matters a lot in probability. When we're talking about 2 dice, we have to think of each individual roll as its own separate event. So even though rolling a 1 and a 6 and rolling a 6 and a 1 both add up to 7, they're actually considered different outcomes in probability because they result from different combinations of those individual dice rolls.
Wow. Okay, so even though the end result might be the same, like getting that 7 the way we got there actually makes a difference. I'm starting to see why understanding these nuances is so important, especially when we're thinking about things like risk and making decisions, right?
Exactly. And that actually leads us to another really important distinction.
So we've covered a lot of ground here, from coin flips to marbles to birthdays. But it makes you wonder, are there any limits to this whole probability thing? Like, are there some things that just, I don't know, defy the odds altogether?
That's a great question. And you're right. While probability can be a super powerful tool, it's not magic. There are definitely limits to what it can predict. Our sources actually touch on this by talking about the extremes of probability, like impossible events versus certain events.
Right, like you were saying earlier with that 6-sided die, there's no way you can roll an 8. It just can't happen.
Exactly.
Yeah.
It doesn't matter how many times you roll that die, you're never going to get an 8. That's an impossible event. And because it's impossible, it gets a probability of 0.
0 for impossible. Got it. So then what about those certain events, the ones that are guaranteed to happen?
Well, those get a probability 1. Like, you roll that same die, you're absolutely going to get a number less than 7. That's a sure thing.
So 0 for impossible, 1 for certain. But I'm guessing most things in life aren't that clear-cut, right?
You got it. Most events fall somewhere in between those 2 extremes. That's why it's so important to remember that probability isn't really about predicting the future with absolute certainty. It's more about understanding and quantifying likelihood.
This is where it gets really interesting, though, because if we start thinking about probability as the spectrum, it can actually help us make smarter decisions in those in-between situations where there are no guarantees.
Absolutely.
Yeah.
Like, let's say you're trying to decide between a couple of different investment opportunities. One promises really high returns, but it also comes with a high risk of failing. The other one offers slower but more stable growth. Understanding probability can help you weigh those risks and rewards against your own personal financial goals so you can make a more informed decision.
So it's not just about playing the odds, it's about using probability to make smarter choices even when we don't have all the answers.
Exactly. And even beyond making practical decisions, Getting a handle on probability can actually make you a more critical thinker in general. Like, if someone tells you there's a really high probability you'll win the lottery, well, understanding how probability actually works can help you see through that kind of misleading claim.
So it seems like probability is about way more than just formulas and numbers. It's really a different way of looking at the world, a framework for making sense of uncertainty and approaching all those what-ifs in our lives.
I think that's a great way to put it. It's about recognizing that even when things seem random, there are often underlying probabilities at play.
And on that note, we'll leave you with this final thought. If even seemingly random events have probabilities attached to them, does that mean anything is truly random? Something to ponder as you go about your day. And hey, keep an eye out for all those probabilities at play all around you. Until next time, keep exploring, keep learning, and as always, happy diving.